now we'll talk about some of the models for multi-axial fatigue. And yesterday I talked a lot about what we see in the material. I have a little bit of review to do before I start with the modeling, and that is just about stresses. What I learned at the beginning when I started doing work in this area is I didn't really understand what the stresses meant. I could do all the calculations and so on. So I want to take a few minutes and talk about that. First of all, there are 6 components of stress and strain that you could have. Actually, there are 9 of them, not 6. Right? If you count the different shear stresses in the picture, then you have a shear stress that acts on each face of the cube in 2 different directions. And the mathematicians like to separate this shear stress and this shear stress. That makes it nice to work in tensors. The engineers realize for this cube to be in equilibrium, these 2 shear stresses, this one and this one, must be the same, or else the cube spins around in space. And so engineers only like to work with 6 dimensions. And the math people like to work in 9. I learned that lesson the hard way. In my PhD thesis, I did finite element modeling of a crack growing through a structure. And I had to have some plasticity modeling. Fine, and so I used all of the standard things. And it came to my PhD defense time. And in the back of the room sits the department head. And when I was all finished, all this very nice fatigue stuff and so on, he quizzed me only about the plasticity, and only if I knew that it made a small difference if all the equations were derived in 9-dimensional space or 6-dimensional space. And of course, I didn't have any idea. So that day, I learned a very, very important lesson. And I want to pass this lesson on to you. Find out what everyone on your examining committee has done in the last year or 2. Even if it's unrelated to your thesis. Even if it's unrelated. Because if I would have had any knowledge, I would have been fine. And so he refused to sign my thesis for some weeks until I learned about 9-dimensional plasticity in deriving these equations. It was a complete waste of my time. Complete waste of my time. But what choice did I have? So I will never forget that there is a difference. There is a difference. Of course, it makes absolutely no difference in the calculations. It's a small term out in the 3rd order, I think, but it makes that difference. So I learned that. So, okay, so we have 6 stresses. We actually have 6 strains as well that we could work with. But I can't deal with 6-dimensional space. I already told you I couldn't do 9 dimensions, and I can't deal with 6 dimensions either. But fortunately, if we want to understand what happens in fatigue, we don't have to deal with all of these. Right? Because when I look at things that are cracked, cracks form on certain planes. I've never seen a crack growing in random directions. Have any of you ever seen a crack growing in random directions? No. A crack grows more or less on one plane, and maybe it will change to a different plane, but it grows more or less planar. So this means that the driving force for fatigue must be more or less planar. And so now if we look at what happens in a plane, so I just draw a plane, then we see that there are only 2 or 3 stresses that you have to deal with. So we look at this plane, and then we, of course, have a normal stress in this direction. And we also have 2 stresses of tension nature which are in the plane, but they are unimportant in fatigue. They are unimportant. I'll show you that later. And then we also have 2 shear stresses. And there are 2 shear stresses only because of the mathematics. Right? We like to think in an orthogonal coordinate system. And then we have 2 shear stresses. But if we wished, we could combine this into 1 shear stress. And that's essentially what happens when you calculate the equivalent stress or Mises stress. You essentially combine both of theirs. So these are the driving forces for fatigue, the stresses that act on the plane. And I say there are only two or three of them. So you are all familiar with the principal stresses. There's how you calculate them. Right? How many of you can solve a cubic equation? Long hand. No one. Huh? No one. Yeah. At one time I could do this because I went to school before the age of the calculator. Yeah. Today it's hopeless. Today it's hopeless. You know, this is why many of the theories are based on equivalent stress historically. Because historically it was so hard to solve this cubic equation to get the principal stresses. And if you don't solve this cubic equation for the principal stresses, then you cannot solve for the maximum shear stress. But solving for the equivalent stress, or Misi stress, is very easy because you can always solve that in terms of the orthogonal coordinate system, sigma x, y, and z, and the various shear stresses. I want to use another stress, and I want to use something which is not so common, and I want to use this maximum shear stress, and I'll just call it tau 13. So you know we have this idea of dealing with the principal stresses, and we say there are no shear stresses. And that's true. If we think about orienting a cube in space, we can orient a cube in space in some way such that there's no shear stress acting on the surface. But there's a very, very large shear stress that acts inside the cube. So it's not that the shear stresses are zero, but if I have a cube oriented in space, such that it's the principal stresses acting on these faces, there are no shear stresses. But if I look inside, on that plane, that has a very, very large shear stress. It's just in a different direction. Okay? And that's this direction tau 13, and so that would be between the two principal stresses, sigma 1 acting in this direction, and sigma 3 acting in that direction. So we'll use that one. So next thing I want to talk about are distributions of stress and strain. When I said that fatigue cracks grow more or less on a plane, I have a fuzzy definition of what a plane is. Right? So if we think about this, and I just load this bar in tension, and I ask you, what is the plane that sees the maximum tension stress? Then of course you will tell me that this is a plane which is oriented in this direction. Right? Exactly in this direction. But what about the stress that acts if I consider a plane that's 1 degree away from perpendicular? Right? How much is that stress? Almost the same. 5 degrees away, almost the same. And so I plot that as I move away from perpendicular. And you can see that I can move away from perpendicular 10 degrees, and that changes the stress by only a few percent. So when I think about a crack growing somehow in a structure, and I think about the plane that it could grow on, it has a choice. Plus 10 degrees, minus 10 degrees, because all those planes will have about the same stress. Right? And what will happen is the crack will choose the weakest plane near perpendicular. And the materials, right, are not truly isotropic. Right? The materials are always a little bit different. So later when I talk about I want to find the plane with the most damage, then I think about the plane I calculate, plus and minus 10 degrees. Because there will be no difference in the stresses until I move very far away. Very far away, much, much farther than 10 degrees. But I also talk a little about the shear stresses, and we can talk about two of them. The one I have drawn here, and this is the maximum shear stress that you have. And some of the theories are based on octahedral shear stress. And octahedral shear stress are the shear stresses acting on the octahedral plane. And that's a plane, if I have a cube that starts at the front on the bottom, the back on the top, across the back to the bottom, and then of course back here. And it's easy to calculate the octahedral shear stress. You can see it there. And Mises stress that you calculate, equivalent stress, is simply the octahedral stress multiplied by a scaling factor. And if you have simple tension, then the octahedral stress is actually smaller than the maximum shear stress. Always. It's a little smaller. I've often wondered why people would use the octahedral stress to do calculations. Why would you choose a stress which is smaller than the maximum? Why? We always look for the maximum stress, right? The maximum stresses should drive the process. Why choose a stress which is smaller?
It's more damaging.
I didn't.
Because it's perhaps more damaging for a person.
Maybe not more damaging, but maybe you want the average stress more than the maximum. You know, Mises works very, very well for yielding. And we think about the difference. So if I want to yield this bar, and okay, maybe this bar has many, many crystals in it, so maybe the average grain size inside this bar is 1 millimeter. So there are inside of this bar thousands of grains. And now I want to plastically deform this. And so if I start to plastically deform this, then the first grain that deforms, right, won't lead to failure. In order for me to plastically deform this entire bar, I have to yield many, many, many grains. Right? So if I have to yield many, many grains, then some kind of averaging process is a better measure than the maximum stress in just one of these grains. So you find for plasticity and yielding, the Mises stress works very, very well. Because you need this smaller stress, this averaging stress of many, many grains. But how about fatigue? See, fatigue is a little bit different. Only one of the grains in this bar has to nucleate the crack. Right? Not all of them, right? Only one of them for it to go to failure. So usually, maximum stresses are a better measure in fatigue, and equivalent stresses and octahedral shear stresses are a much better measure for plasticity. You know, that's the real difference. And you can see it's different by only a few percent in tension. But if you look at things like torsion, it could be different by 18%. 6% in tension, and again 6% in biaxial tension. So if I have a real component, let's say the wheel on my car, okay? What is the precision that I know the stresses? How accurately do I know the stresses on the wheel of my car? 10%? 50%? Yeah. Okay? Yeah. So this is why people use the Mises stress, even for fatigue. Because they say, yes, we understand that it is different, but in the precision that I know the loads and everything else, it's not the dominant variable. So you'll see a lot of people do it. And a lot of people say, you know, it works good enough. It works good enough. Okay, so that's the difference between the two. Right? And I'll show you theories based on both. So throughout the day I will draw little pictures, and so I like to draw and just review Mohr's circle for different states of stress. So this is just tension, and so we have Mohr's circle for tension, stress, shear stress. Principal stress is in the direction of loading. Second and third principal stresses are 0, and the maximum shear stress is half of the principal stress. And we can also look at Mohr's circle for strain. Mohr's circle for strain, in order to plot this as a circle, then you have to plot the shear strain divided by 2. Quiz for PhD students. Why is it divided by 2? To make it all work. No one remembers from the first year studies. It's a good quiz question. No one ever remembers why it's divided by 2 to make it a circle, right? Yeah. Oh, multicolored. Right? So there's the original cube. And when you shear the cube, in pure shear, it goes something like that. And there's shear strain on both sides. And to differentiate this case from this one, there's shear only on one side. So that's where the math comes from. And like you, I can't derive it all, but that's the concept behind it. In pure shear, you can shear on both sides like that. So anyways, that's always divided by 2, and that's how I remember it. I remember the funny little diagrams. Okay. So of course, when I pull on this, then there's Poisson contraction in the other directions, and I always have some strain there. And this is torsion. And if you have torsion, of course, and I twist this bar, well, I need it. This elliptical bar bothers me, so I'm going back to my round bar. There we go. It just looks wrong to talk about torsion of an elliptical bar, doesn't it? Okay, so I twist the bar like this, and of course I have the maximum shear stress exists on this plane and this plane, and the maximum principal stress exists on planes which are 45 degrees apart. And so that you know. And if you draw Mohr's circle, then Mohr's circle for torsion actually looks like this, with 2 smaller circles inside. And that is, I could also look at a shear stress instead of looking at one that's here and one that's here. If I look at the end view, there's also one that goes in 45 degrees, something like that. And if I look at Mohr's circle for strain, then Mohr's circle for strain in torsion looks like this. And you get that the shear strains are 2 times the principal strain. And here you get that the principal stress is equal to the shear stress. So let's just think about what this tells us a little bit. Right? When I load this in tension, right, and I nucleate a crack in shear with some stress level, okay, whatever it is, the shear stress that acts on this plane is only half as much. So once a crack starts to form, then there's a big tendency to try to turn and grow into tension, because the tension stresses are twice as high as what the shear stresses were. And if you look at something in tension, you find that cracks nucleate and very quickly turn to try to grow in mode 1 in tension. Well, we do the same shear stress now, and we do an experiment, and now we twist in torsion. Okay? And now we twist in torsion, but now in torsion, the tension stresses that act on a 45-degree plane are only half as much as they were in tension. So there's not such a tendency to try to turn immediately. So you'll find much longer shear cracks in the torsion test than you ever do in a tension test. Just because the same shear stress acting in tension and torsion results in 2 different tension stresses on the other planes. Okay, so that's tension and torsion. Right? This is biaxial tension. So biaxial tension, I pull in both directions. And of course, these two principal stresses are equal. This one is 0. And so if I look at this as being the plane of the material, and I load this plate like this and load it like that, there's no shear stress at all acting in this plane. Right? But there is a big shear stress that acts through the thickness. So when you look at something that's been loaded on biaxial tension, you find cracks that form at 45 degrees, but they go 45 degrees into the material, not on the surface. And if you look at Mohr circle force strain, then Mohr circle force strain loading with the same principal stress in all three examples, then you find that the maximum principal strain for the same stress is actually smaller in biaxial tension than it is in tension. And the minimum principal stress is smaller in compression. By the way, this means that if I use the strain as the damage criteria, there's a big difference between loading something in tension and biaxial tension. Sure. All right, let's look at that. So let's think of a real scenario. Let's take this tube like this, and I'm going to pressurize the inside of the tube so that I have a constant hoop stress. Okay? And when I pressurize the tube for that constant hoop stress, then I'm going to start applying an axial stress to this tube. Okay? And that's what happens as I apply the axial stress. So when I pressurize this tube, and I just work out the numerical example, the magnitude is not important, only the relative strains. So we end up with this hoop stress, and then of course when I load this with the pressure on the inside, then the tube becomes smaller in length from Poisson contraction, and that's shown down here. And then as I load this in axial stress, and I increase the axial stress, of course the axial strain goes up, but the hoop strain goes down. So that means if I want to have longer lives, I should always apply a biaxial stress. Because if I apply a biaxial stress, then the strains will go down in the other direction. Absolute nonsense. Right? It's a true statement. The strains go down. But the strain alone is not the driving force for fatigue. You have to have stresses as well. Both become important. Both become important. I'll come back to this and I'll show an example. By the way, this is a case where you can make a serious mistake in doing fatigue assessments if you only look at the strains. Because this strain is 20% less than the other one. If I increase the strain, decrease the strain by 20%, how much does that affect the fatigue level? About. Factor of 2, factor of 10. How much does a 20% difference in the driving force make? You all would have trouble if I was on your PhD committees. Because these are the questions, I like to ask these questions, about how much, right? Okay, we can answer this question. All right? So, I have the strain, right, versus the lifetime, right, like that. What is this slope? What's a reasonable number for that slope? Or stress if you like. Much trouble on the PhD exam. The funny thing is, I would just tell you these stories. I really do ask these kinds of questions. And the students, right, the good students will stop and say, I don't know. The not so good students will turn to the blackboard and try to derive something. Okay. Yeah. And then, of course, when they try this makes it worse. Because then I ask more questions. Okay, so, you know, if you look at fatigue data, right? So maybe this slope is minus 0.2 or maybe minus 0.3 or something like that. Right? Something like that. So that means that if I change this by 20%, that it's 20% raised to this power. Okay? So if I answer my question, then 20%, 1.2, and well, I don't know. Let's use this one. Minus 0.2 turns out to be what, fifth power dependence? So what is 1.2 to the fifth power? He will work this out. No. What are you doing? You're not with your calculator working out my quiz? It's about 5, I think, if I remember. So, you know, whether you choose to think about, all right? Is it 5? 2.5. 2.5. Yeah, not too bad. Yeah, I forget the answers. But again, going back to the PhD students, they are clueless, so. See, you will never forget this now, right? 20% change will move the lifetime two and a half times, right, by missing that. So it does make a big difference if you work in stress or strain, if you work only in one dimension, because all the strains are connected. All the strains are connected. Okay. I always like to talk a little bit about the shear stresses and to just look at the difference between the principal stress and the equivalent stress that you calculate. And you know, if the shear stresses, if the ratio of shear stress to tension stress applied on my tube, if that ratio is only a third or so on, then it doesn't matter which stress you pick, right? They are about the same. The time it matters when you deal with either equivalent stress or principal stress is when the shear stresses dominate, way out here. Then there's a big difference in these two stress levels. Okay, so there's a quick review of the different kinds of stresses that we will work with. The first concept that I need a lot today will be this one I talked about, the different stresses that act on a plane. And then these are things only in nomenclature. So that when we talk about principal stress or maximum shear stress or octahedral shear stress, then you have some understanding of what they are and what they mean and how they are different. So I now want to go on to the actual stress-based models. And I like to talk about 3 of them. I suppose if I go to the literature, I'll find more than 100 models. Probably more than 100. So why do I choose these 3? I choose these 3 because they are representative of all of the 100 models. Why can only 3 be representative? Well, let's think about this a little bit. So first of all, almost all of the experiments come from doing tension tests or torsion tests or some combinations of tension and torsion. Okay. So if you look at this, then if the loading situations I can deal with are tension and torsion, I have only two variables, right? Shear stress, tension stress, and of course the ratio between those two. How many ways can you combine two variables? I can add them, I can multiply them, I can square them and take the square root. There aren't very many. There aren't very many ways of combining these. But what you find in the literature is that people make very small changes to the fundamental models, and then they publish this as a new model. And another one, and another one. And the only people who use these models are the professor and one of his graduate students. No one else uses them. And so I choose these models because these three are widely used. They are very widely used by many people. Yeah, I call this publishing. This is the conference syndrome. If it's a very nice conference in the wintertime on the Mediterranean, then you must submit a paper. So you can go to this very nice weather in the wintertime. Sure, of course. And so then you make a small variation of the model and publish yet another one. But no one uses. So let's look at these three. So first we look at what the test data shows. And of course all of the early test data were combinations of torsion loading and tension loading. And that goes back to the problems really in the power transmission. So if you look at the early fatigue problems, were all about transmitting power through a shaft with some gears or belts. And if you look at a shaft, the only way to load this is combinations of bending and torsion. And of course, if you do a fatigue test, it's much easier to do a bending fatigue test, a rotating bending test like Voller, than it is to do a cyclic torsion test. And so people wanted to know, what is the torsion fatigue limit, given that I know the tension fatigue limit? And then of course there were lots of tests where people actually tested in torsion and combined tension. And this is a plot of just some of the early data. It actually comes from Goff. And on this axis I'm going to normalize the shear stress in bending divided by half of the bending fatigue limit. Okay, why half the bending fatigue limit? Well, of course, if I calculate the fatigue limit from a tension test, the shear stress during the bending test was half the tension stress, so that's why the half. And on this axis, the shear stress in torsion, again divided by that same half the bending fatigue limit. Remember, I told you that when I load this in tension, that in tension, the shear stress is half the tension stress. But if I load this in torsion, the shear stress is equal to the tension stress. And so if the principal stress were the correct criteria, then of course everything would fall on this line. And if the maximum shear stress is the correct criteria, everything would fall on this line. And if the octahedral stress is the correct criteria, everything should fall on this line. And if you look at a lot of the test data, you'll see that the test data falls in here. Right? So if I look at this chart, then I would say that the octahedral stress is a good criteria for fatigue. And what other conclusion would you make from this? It is the best criteria. Now, in the next few minutes, I hope to convince you that that's wrong. This is what I call the spreadsheet mentality. Spreadsheet mentality. I take all of the data, I put it in a spreadsheet, and I calculate the correlation coefficient. And whichever theory has the highest correlation coefficient must be correct. So that's fine, but that means I can never use this theory to extrapolate outside the data. But if I have a loading situation for which I know the data, I don't need to do calculations. So the real value in any theory for fatigue or anything else is to be able to extrapolate outside the range of the data. What good is it to have a theory that you can't extrapolate outside the range of data? Right? And I want to convince you that this is a mistake. Right? Okay? So let's look a little bit more about the test results. And we can think about doing different kinds of tests. And so, of course, the first test we might do is we simply cycle this bar in tension, and then we also can cycle this bar, and we can have a static tension or a mean stress that's on it. And these are the traditional fatigue tests. But I also could first twist the bar with a static torsion, and then I could do tension fatigue tests with a static torque. Of course, then there will be a mean shear stress to the text on this bar. And then I can also think about doing a cyclic torsion test with the torsion mean stress. And I can also think about loading this bar in tension and then doing the cyclic torsion test. And that's exactly what was done. And let's look at the results from that. So when I look at the results, and so this is a plot, and this is the data that science assembled, and this is the axial stress divided by the fatigue strength, and this is, of course, so we can plot many different materials, and that's what the different symbols are. And on this axis, we plot the mean stress divided by the yield strength. This is essentially a Goodman diagram. And you have the expected behavior, that if you have a compressive mean stress, then either the fatigue life is increased or the allowable stress range is increased. And if you have a tension stress, then the allowable stress is either decreased or the life is decreased. Right? Well, how about the other case? Suppose we have just put a static torque on here, and of course that will change all of the stresses. The principal stresses will increase and so on. But I'm cycling it only in this direction. And if you look at this, then we can plot the shear stress now divided by the shear. I've got the wrong one. Right? So I have torsion, and now I'm simply going to test this with a mean torque. Right? And when I do that, then you can see there appears to be no effect until you get well past the yield strength. So first of all, what is the effect of a mean shear stress? What is the difference between a positive shear stress and a negative shear stress? Well, let's think about, just not from the math, but let's first think about what is the difference between a positive tension stress and a negative tension stress as it relates to fatigue. So we can think about our ideas that, well, we understand that small fatigue cracks form in shear like this, right? And so if I have a positive stress acting on this shear plane, a positive stress will tend to pull this apart. Remember the pictures I showed yesterday of cracks opening and closing and sliding, right? So I can visualize that this positive stress really physically means that I'm opening up the little micro cracks. And of course, when I calculate a negative stress, right, a negative stress means I am trying to compress these little micro cracks. So I understand, at least conceptually, the difference between positive and negative stresses when they are tension. But what is the difference physically between a positive shear and a negative shear?
Direction.
Yeah, only direction, right? Otherwise, there's no difference. Right? Only direction. Twist clockwise, counterclockwise. Okay? So we expect no change of positive and negative, but even if we took the absolute value of the shear stress, you can see absolutely no effect until you get above the yield point. So we might conclude that there is no effect of a mean shear stress on fatigue from this data. And this data here is very unreliable for calculating the stresses. Why? Well, you know, when people did these tests, then they always reported the stresses from the elastic solution. So I test a round bar, and they take the torque times C divided by J and calculate here is the stress. Well, what happens when the bar yields? So, of course, the stresses on the surface will not be what the elastic solution is. Right? The stresses will be limited at the yield strength. So I expect that this data incorrectly calculates the stresses from the elastic assumption. Nevertheless, we might conclude that the mean shear stress has no effect in torsion. No effect. So this is cyclic tension with a static torsion. So cycle this in tension and then have a static twisting. And we see the same kinds of behavior. You know, nothing happens until you get way out here, well past the yield point. So it seems from the test data that if I have a mean shear stress, it does not affect the tensional fatigue, and it also does not affect torsional fatigue. Right? So mean shear is unimportant. And then we do the last one. And the last one is to cycle this in torsion. So twisting like this. And now we apply a mean tension. Right? So let's think about this a little bit. Right? I'm going to cycle this bar in torsion. And I think about how is this going to behave in fatigue. So when I cycle this in torsion, then I know that I will form some small little microcracks on planes that look like this, because this plane sees the maximum shear stress. And what happens if I pull this in tension? Right? The small cracks that form here are going to be opened up. Remember my pictures about all that rubbing and so on. But if I apply tension, I will eliminate all of that friction. Right? And so this should be very detrimental. Right? And if I push on it, right, then I will increase the friction that's there, and that should be very beneficial. So that's what we might expect. And that's what you see in the data. Right? So it is beneficial when you have compression, and it is detrimental when you have tension. And so these are observations from many, many researchers, and this is what Sainz summarized. So the conclusions I make from this data are that a tension mean stress affects both the tension and torsion behavior, and a mean shear stress, right, doesn't affect either one. All right. Now, how would you like to combine these into some theory? You have your choice, right? So first of all, you say, okay, I need to do something about the shear stresses, because I know shear stresses are responsible for fatigue. Would you like to use the maximum shear stress or the octahedral shear stress? Either one, right? They're not so different. Right? So I want to say, okay, I know I need the cyclic shear stress. Right? And what about the mean stress? Well, if a mean torsion is unimportant, right, what are the stresses in torsion? So I think about the stresses in torsion. So in torsion, of course, I have the first principal stress equal to whatever the shear stress is, and I have the third principal stress is equal to minus the first principal stress. Okay, so those are the three stresses I have to work with. And then what science said was, oh, this will be easy, because I could just use the hydrostatic stress. Right? So you remember the hydrostatic stress is simply the summation of the principal stresses. So the hydrostatic stress is the first stress invariant. All right? Well, now this is easy because the first stress invariant in torsion is always 0. And my observations are that a torsional mean stress has no effect. So why not use that? And this was exactly Sine's logic. It's exactly what Sine's logic. Sine said, take the octahedral shear stress, which is easy to calculate because you can calculate this from the individual components of the stress. And now we're going to make a modification to the octahedral shear stress, and we're going to use the hydrostatic stress, sigma 1 plus sigma 2 plus sigma 3. Right? This 3 balances that one. And then, well, you know, every fatigue theory needs an adjustable constant. And so, well, you have an adjustable constant here, alpha, kind of a scaling constant. And, well, sure, because I can test different materials, and some have more sensitivity to mean stress than others. And so, okay, there's my scaling constant. And I set that equal to some property of the material. And this property of the material will be the fatigue limit normalized to the octahedral shear stress. Okay? And this was exactly Sine's logic. So, you know, people have the idea that there's some theory behind fatigue models. I would say there's absolutely no theory behind any fatigue model. I know that's not very comforting, but, you know, these fatigue models come from people making observations. They make observations of the science, and they propose some mathematics that puts the variables in the correct place. Nothing more. And if you actually read Sine's paper, Sine's tried several variations. He said, what if I use the maximum shear stress? And he plotted the data and said, oh, it's about the same. And what if I use the maximum stress instead of the hydrostatic stress? And he plotted the data, and it's about the same. And then after doing these different kinds of comparisons, at the end he says, I recommend this form because for a general stress state, it's the easiest one to calculate. It's not better than the others. It's not particularly worse than the others, but it's the easiest one to calculate. Okay? So why is the science model used by many people? It's easy. Sine was a professor at UCLA, and he had many, many graduate students. If you have many, many graduate students, then they go out to work, and they publish even more papers, and you know, it's kind of like water running down the hill. And then once the theory gets established, then even more people use it because it goes into textbooks and so on. But there's no theory behind it. Only these observations that I showed you. Only these observations. And it's still widely used today. Right? And it works okay. I'll show you cases where it doesn't work, but it works okay. Right? So let's go to the next model. And Finley's model. Both of these people worked at the same time. And this work was all done maybe in 1960, I think, about. I think that's right. I think 1960. Finley's idea was different. So Finley said, look, there's a big difference between tension and torsion. What is that difference? Well, there's more circle for tension and torsion. Right? So I have the bar, and I'm going to load this in tension. And of course, we know that maybe a fatigue crack will form on a plane which is oriented 45 degrees to the axis. And let's look at what happens on this plane. So when I load this in a tension cycle, then I, of course, have a shear cycle that acts on this 45-degree plane. But in addition to a shear cycle, when I load this in tension, I also have a tension cycle on the same plane. So when I have a shear crack in tension, I'm not only shearing this crack, but I am opening it at the same time. And we see that for Mohr circle. So here is Mohr circle for tension. Right? And there's the maximum principal stress, the loading stress. 45 degrees away, I have the maximum shear stress. But on this same plane of the maximum shear stress, I have a normal stress that is the same magnitude as the shear stress. So I think just about tension, and if I think about this now in fracture mechanics terms, I have on this 45-degree plane, I have a mode 2 cycle, but at the same time I also have a mode 1 cycle at the same time. Okay, that's what happens in tension. And now let's look at torsion. So I'm going to twist this now with the same shear stress. Right? But when I look at torsion, right, okay, I have the principal stress and the shear stress is equal to this principal stress. Fine. But on the failure plane, right, on this plane, the normal stress is 0. So if we think about the picture we are developing for how the fatigue process works, this should be much more damaging than this for the same value of the shear stress. Because in tension, I am shearing this with a mode 2 cycle, but I also have a mode 1 cycle at the same time. And this mode 1 cycle will eliminate the crack face friction and so on, as we have discussed. Right? And that was Finley's idea. Okay? And then he wanted to express this from the idea, and so he said, fine, the driving force for fatigue will be the maximum shear stress. Sure, why not? You know, maximum stress in a grain makes a lot of sense. But the normal stress will also have some effect. The magnitude of the normal stress. And he, of course, combines this in a linear way. And, of course, with a scaling constant K in it. And then you set this to the fatigue limit that you like in tension. Again, normalized back to the correct value of the shear stress. By the way, you have to be a little bit careful with these theories. Of course, if I choose K equals 0, this becomes the maximum shear stress theory. And if I choose K equal to 2, this becomes the maximum principal stress theory. Isn't it? Just a little quirk. Yeah, it happens. But K generally is in the middle. Right? K generally has values of 3. So that's Finley's idea. The Finley model, again, published about 1960. Almost no one used this until maybe 10 years ago. And 10 years ago, it has now got a lot of use. Why wasn't it used? Finley was also a professor. But Finley worked by himself without very many graduate students. And so if you look at the Finley papers, there's only 3 or 4. And there are no graduate students who use the model and so on. So it was lost in the literature to just be this one little bit of work. But as people got more interest in it, then this model has become very, very popular. Very, very popular. Yeah, it's a good lesson about having students. You need many of them. You need many, many of them.